Section 3.6 here in geometry might be really important and it might not, practically speaking, depending on whether or not we're doing formal two-column proofs this particular year or not. But either way, it's a good idea to go through some stuff that's mentioned here in 3.6 because these are kind of the building blocks that we're going to use to establish a lot of important concepts with lines and angles later on in this chapter. So the title of this section is Proving Angle Relationships, and that word proving kind of suggests that we're going to be doing proofs. We at least want to talk about some of these things and see why they're true, even if we don't end up doing formal two-column proofs. So the first thing we're going to begin with here, I'm just calling some helpful reminders of things that we already know from what we talked about earlier on in chapter 2 with angles. And your teacher may or may not have introduced this concept in the past. The first one we're going to talk about is postulate 3.10, called the protractor postulate. Now I want to remind everybody, hopefully we learned this back in chapter 1, that a postulate is a mathematical idea that we know is true, but it can't be formally proven, sometimes called an axiom as well. And that's what this protractor postulate is. It says something very simple. Every angle has a measure between 0 degrees and 180 degrees. It essentially says that every angle can be measured. And you guys hopefully know that we've got 4 different types of angles. We have an acute angle that's less than 90. We have a right angle that's exactly 90. We put the little corner mark there. We have an obtuse angle that's more than 90 but less than 180, and then of course there's the straight angle, which is exactly 180 degrees and really just looks like a straight line. So that's postulate 310. It says something basic, we all know it's true, it just is so simple that it can't be formally proven. A second postulate here, 3.11, is called the angle addition postulate, and this is one you've been using probably for weeks already here every time we deal with angle measures. When we are dealing with overlapping angles, like we have in this figure right here, and I should have labeled this ahead of time, let's see, if I called this A and this B and this point C and this point here D, this is a diagram that hopefully you guys recognized before. We actually have 3 angles here. All right, I'm going to call this first angle here angle 1, an angle 2 right below it, and then angle 3 is this larger angle here, ABD. That's the overlap of the first 2. And the angle addition postulate says that the measure of angle ABC, which is what I've called angle 1 here, that first smaller angle, can be added to the measure of angle CBD, which is this second smaller angle here. And that will equal then the measure of angle ABD, from A to B to D, the large angle here. So usually what we want to say here is little angle plus little angle equals the big angle here on the outside. We've used that already earlier on in chapter 2, so hopefully that's one you guys are relatively comfortable with. Okay, so those are things that we already learned here back in chapter 2. Moving on right here, the second part of our notes, we're going to say that we're going to formalize now some things that we already kind of learned. And this particular textbook introduced these in kind of an informal way, just kind of said things as a statement. Now we're going to actually write them down as theorems. Let me take just a second to remind everybody that a theorem, just like a postulate, which we had on the last slide, both of these are mathematical statements that we know are true. But the difference is that a theorem can be, and therefore has been, formally proven, whereas a postulate is just something that we know is right, but we kind of have to take it on faith or on common sense. So theorem 3.3 is the supplement theorem, and it says the following. If 2 angles form a linear pair, that's a vocab term we should know from chapter 2, if 2 angles form a linear pair, then they are supplementary angles. And if we recall, a linear pair is 2 adjacent angles whose non-common sides are opposite rays. That's exactly what we have in this figure right here, guys. We've got a common endpoint right here in blue of 3 different rays. We have one ray going up and to the right, another ray going in the exact opposite direction, bottom left, and then a third ray just kind of randomly sticking up here like that. So we have 2 angles, one here and one right here that together make a straight line. This is what we call a linear pair. And while we said this early on in Chapter 2, now we're stating it more formally here with a theorem. If these two angles, the 12x plus 13 and the 50 minus 3x, if those two angles form a linear pair, then they're going to be supplementary. So when our directions say solve for x, we look at the theorem, we recognize that yes, this theorem applies because we are dealing with two angles that form a linear pair, and then we use the then part of the theorem to make an equation. These angles are supplementary. And what does the word supplementary mean? Add up to 180 degrees. So here's going to be our equation, everybody. We're going to have a 12x plus 13, that's one angle, plus the second angle right next to it, 50 minus 3x, and that's going to equal a sum now of 180 degrees, because that's what the word supplementary means. All right, so with that in mind, let's solve this one quickly. We're going to combine some like terms here. 12x minus 3x is going to give us a 9x, and then with constants, a positive 13 plus 50 is going to be a plus 63. All that will equal 180. We're going to subtract a 63 from both sides here. Those will cancel out. I'm going to move over here to the right now. That's going to give us a 9x is equal to, and I believe that is going to be a 117 there on the right side. And we'll divide both sides by 9 now, and we are going to get x equals, oh, and I'd hate to make a mistake here, but I'm pretty sure that's 13. Let me check that real quick, guys. 117, here's my calculator. What did I want to do? We'll make that a little bigger and easier to read here. 117, missed a 1 there, and we're going to divide that by 9, and yeah, that's going to give us 13 then for that value for x. Now, what you should always get in the habit of doing in geometry, make sure you've answered the question that they asked. They wanted us to solve for x, and we're done with this one. But even though they didn't ask for it, it is always a good idea to plug that value for x back into the original expressions and make sure everything works. So let's try to find the value of this angle right here, 12x plus 13. So that is going to be 12 times an x value, we believe, of 13. So there's your 12x, and we'll add another 13 to that, and that gets us an angle of 169 degrees. Bigger than I thought it would be, but it's less than 180 still, so that's still possible. Let's check this second angle now, 50 minus 3x. So that is going to be 50 minus 3, and we believe that x is 13. Okay, and we'll hit enter, and we get 11 degrees now for the measure of this angle over here on the right. Smaller than I thought, but still between 0 and 180. And the one thing I want to make sure of now, do these two angle measures make sense relative to one another? Well, hopefully you notice that if we added 169 plus 11, that's going to get us 180 degrees. And since we're dealing with a half circle right here on that straight line, yeah, that 180 is what we should get. So I feel really good about this answer right here of x equals 13. Okay, that's the supplement theorem. As you might have guessed, there's a complement theorem that comes right after that one. And the complement theorem says that if the non-common sides of two adjacent angles form a right angle, that's important, then the angles are complementary. Now, on the previous slide, we spoke about how supplementary means adds up to 180. Complementary means two angles that add up to 90 degrees. So if we see a right angle right here, and we've got two adjacent angles that would add up to that, we're dealing with complementary angles. So let's take a look at this diagram right here. Now, what's hopefully obvious is that once again, we have a straight line down on the bottom, which means that this entire half circle right here is going to be 180 degrees. And we can see this right angle that's drawn here on the left, which means that that is 90 degrees. Therefore, the entire right side of this figure, here and here put together has to be 90 degrees as well, because 90 plus 90 is going to get us the 180 that we need. So now if I go back to the theorem here, if the non-common sides of two adjacent angles, well, here's one side right here, and then here's a second side. These are the non-common sides, and here in red would be the common side right there. If those non-common sides form a right angle, which they do, then these two angles here and here have to be complementary, meaning they have to add up to 90. So here we go, guys. We're going to get a 4x plus 9, and we'll add to that. That's a 3x minus 10, I think, before I wrote all over the thing. Yeah, 3x minus 10, and those two angles now have to add up to 90. We'll combine some like terms again. The 4x and the 3x are going to give us a 7x. Ooh, we've got a positive 9, be careful now, and a negative 10. So that's going to be minus 1 equals 90. We'll add that 1 on both sides here and get 7x is equal to 91. And then we'll divide both sides by 7. And good news, bad news. Good news, this works out evenly. The bad news is 91 divided by 7 is 13, which is exactly the same answer I had for the previous problem. That won't normally be the case. Now again, the directions just say solve for x, so I think we're done, but we'd probably want to double check that here. 4x plus 9. This I think we can do in our heads here. 4 times 13 is 52, and 52 plus 9 is going to get us 61 degrees for the measure of this angle here. 3 times 13 is going to be 39, and 39 minus 10 is 29 degrees. And if we take a look at these two angle measures here, 61 plus 29, well, the 1 and 9 is the 10, carry the 1, 6 and 2 is 8, plus that 1 up on top is 90. That's exactly what we should have. So feeling good about that answer there as well. So that's the complement theorem in action. Look for right angles within your figure, and if you have some then, if there's two adjacent angles that together make up a right angle, yeah, they have to add up to 90. All right, next one here, Theorem 3.8. This is an idea we used a lot early on in Chapter 2, the vertical angles theorem. This one, is, as far as the verbiage goes, is pretty straightforward. If two angles are vertical angles, then they are congruent. And if you recall, vertical angles are two non-adjacent angles, not right next to each other, formed by two intersecting lines. So if we take a look at this diagram that we have right here, two intersecting lines, and there are 1, 2, 3, 4 angles that are formed there when you cross two intersecting lines. And the vertical angles are the ones not right next to each other, but across from one another. Angle 1 and angle 3 are vertical angles, so this theorem tells me that angle 1 is congruent to angle 3, but also 2 and 4. So I'll put a double tick mark here and a double tick mark here. Angle 2 and angle 4 must be congruent to each other, so their measures are going to be equal. That means that 8x minus 11 has to equal 2x plus 43. This angle here and this angle here, they look the exact same size, and they are the exact same size. So we'll solve this by subtracting 2x from both sides, and at the same time here, I'm going to add an 11 left and right. 11's on the left cancel, 2x is on the right cancel. 8x minus 2x is 6x, and 43 plus 11 is 54. We'll divide both sides by 6. This worked out nicely, and hey, look, it's not 13 this time. X is equal to 9. Now again, even though the directions didn't say, always a good idea to plug that value back in and see what you get. 8 times 9 is 72. 72 minus 11 is going to be 61 degrees. And let's check it over here. 2 times 9 is going to be 18. 43 plus 18 is going to be 61 degrees as well. And since both those two angles are congruent, they're both 61, I feel pretty good about that. Okay, if we wanted to find the measure of angle 1 now, we would recognize that these two angles here, angle 1 and angle 2, form a linear pair. They're supplementary, so we would just take 180 minus the 61 that we just came up with, and we'd get 119 degrees for the measure of angle 1, and 1 would have to be congruent to 3, so this would be 119 degrees as well. And as one last check, you could add up the measures of all four of these angles here, and you should get 360 degrees because all four of them together would make one complete circle. All right, hopefully all that makes sense. A nice thing about math, and specifically geometry, there's a lot of different ways to attack these problems, but they all should get you something at the end that makes some sense. Okay, on to some new theorems now, things that were not discussed earlier on in Chapter 2. This theorem, which is really three little theorems put together, but your book just calls it one, Theorem 3.5, this might be really important if you're doing formal two-column proofs. Admittedly, it's going to be much less important if you're not doing proofs. So here we go, guys, the three properties of angle congruence. The first one right here, the reflexive property of congruence, sorry for my spacing here, guys, every angle is congruent to itself. It basically just says that angle, I'll make up a new number here, angle 5 has to be congruent to angle 5. Why? Because whatever the measure of angle 5 is, it'll be equal to the measure of this angle 5 because it's the same angle. That one's pretty obvious, I think. The second one here, also pretty obvious, the symmetric property of congruence. If you have a statement of congruence with angles, if angle 1 is congruent to angle 2, then if it benefited you, you could flip that around a little bit and say then angle 2 has to be congruent to angle 1. Now that seems really, really obvious. And it's true with equations as well, guys. If I were to say that 2 plus 3 is equal to 5, which it is, you could flip that around and say, okay, then 5 is equal to 2 plus 3. So congruence and equality both have symmetric properties. What doesn't have a symmetric property? How about something like less than? 9 is less than 13. True statement. But you can't just flip that around and now say 13 is less than 9. That statement right there is not true. So certain operators, certain comparative statements have a symmetric property, but not all of them do. Okay, and the third property right here, the third, there you go, is definitely the most useful of the three, the transitive property of congruence. If we know that angle 1 is congruent to angle 2, and we also know that angle 2, which is the second angle here, right, but the first angle here, if angle 2 is congruent to angle 3, that allows us to draw a direct connection between angle 1 and angle 3. Angle 2 is kind of an intermediary right there, and it allows us to conclude that angle 1 is congruent to angle 3 because they're both congruent to the same thing, which is angle 2. As I said, these properties aren't super important if we're not doing proofs here, but they're good to have in your notes. They certainly won't hurt. Speaking of which, two more properties like this, or two more theorems that again aren't going to be super useful if you're not doing proofs. Theorem 3.6 is the congruent supplements theorem. Angles, and usually we put a 2 in front of there, it doesn't have to be 2, but two angles that are supplementary to the same angle are congruent to each other. Now very quickly, I don't want to dwell on this one too long, but you could kind of illustrate this pretty well if we drew two intersecting lines. Now, if we do that, this is the same diagram I had 2 slides ago, you form 4 angles. 1, 2, 3, and 4. Now, two angles that would be supplementary to the same angle. Let's think about that. We have a straight angle here encompassing 1 and 2. So we could say now that angle 1 and angle 2 are supplementary. They form a linear pair there, so the measure of angle 1 plus the measure of angle 2 has to equal 180 degrees. However, let me switch colors to green now, guys. We could also say, let me draw a half circle here. We could also say that 2 and 3 form a linear pair as well, just looking at a different angle. So angle 2 and angle 3 are supplementary as well, which is to say the measure of angle 2 plus the measure of angle 3 also has to equal 180. So let's look at what this theorem says. If angles are supplementary to the same angle, they have to be congruent. Well, what do you notice here, guys? There's an angle 2 and there's an angle 2. Angle 1 is supplementary to angle 2, but so is angle 3 here. So angle 1 and angle 3 are both supplementary to the same angle, that being angle 2, and therefore these two angles then have to be congruent. So if we put all that together, we would say that angle 1 must be congruent to angle 3. And if we look at the diagram, I think we know that already. Angle 1 and angle 3 have to be congruent because they are both, let me go back to red here, they are both vertical angles with one another. And that takes us back to the theorem we talked about 2 slides ago, the vertical angles theorem. So the reason this is a theorem and not a postulate is because we just proved it true using an existing theorem. All right, that's the congruent supplements theorem. The congruent complements theorem says pretty much the exact same thing. Angles complementary to the same angle are congruent to each other. So if you wanted a diagram right here, here's what I think I would draw. Notice as soon as we're talking about complementary angles, you shouldn't be surprised here, I'm drawing myself a right angle. In fact, let me go right now and put a corner mark right there. And then I'm going to put a third ray kind of sticking up here like that, and I'm going to say this is angle 1, and this is angle 2. So right now, I would say that angle 1, let's go with this. Angle 1 and angle 2 are complementary angles, meaning that they add up to 90. But now, let me switch to purple right here, guys. Now, I'm going to kind of redraw this ray right here, and I'm going to try to draw another ray sticking out like that. Now, what I was hoping to do there, and that you guys would see, is that I drew another right angle right here. So I'm going to call this, let's see now, angle 2, and this one angle 3. Now it looks like 2 and 3 are complementary as well. So angle 2 and angle 3 are also complementary. They are going to add up to 90 degrees as well. And let's look at this theorem now. Angles, and again, usually we say two angles, that are complementary to the same angle. Do we see it, guys? Angle 2 and angle 2, the same angle. If there are two angles that are complementary to 2, they have to be congruent to each other. That would be angle 1, and that would be angle 3. And I think we can hopefully see that from the diagram. Angle 1 and angle 3 are going to be congruent. This doesn't prove anything, guys, but we could see it numerically if we were to say, just for the sake of argument, that angle 2, I'm just going to make something up here, was 70 degrees. Now, in order for 1 and 2 to be complementary, how big would angle 1 have to be? Complementary means adds up to 90. So 90 minus 70 would be 20 degrees for the measure of angle 1. But now if we look at this statement, angle 2 and angle 3 are complementary as well. They have to add up to 90. So if 2 is 70, to find the measure of angle 3, this is going to sound familiar, we would take this 90 minus that 70 and get 20 degrees here also for the measure of angle 3. That just kind of numerically supports this idea then that angle 1 would have to be congruent to angle 3. So that kind of illustrates the congruent complements theorem. Okay, the last slide that we have right here can take a little while to get through. There's 5 theorems on this slide, none of which is really like earth-shattering in its importance or its difficulty, but definitely good things to have in our arsenal as we're moving forward so that we're not making assumptions. Let's go through them quickly. Theorem 3.9, perpendicular lines meet to form blank right angles. Well, our definition of perpendicular lines would be two lines that intersect to form a right angle. So here are my two perpendicular lines, and I'm going to go ahead and put a corner mark in here now to say, okay, angle 1 is a right angle. But I want to talk then about angle 2 and angle 3 and angle 4. What do we know about them? Well, angle 1 and angle 3 are vertical angles, and we learned a theorem a while ago that said vertical angles must be congruent. That means that angle 3 has to be 90 degrees as well. Well, that's nice to know. How about angle 1 and angle 2? Together, they make a linear pair, which means they're supplementary. So we would take 180 minus the 90 degrees that we have right here for the measure of angle 1. Oh, and that leaves us 90 degrees for the measure of angle 2. That is a right angle also. And if angle 2 is 90 degrees, angle 4 is vertical with that. That would have to be 90 degrees as well. So what we're supposed to see here, guys, is when you have two lines, if they meet to form one right angle, you actually know that all of the three other angles are right angles as well. So what's missing in this line? Perpendicular lines meet to form four right angles. Anytime you have one right angle, you actually have four if you just extend everything and make lines out of them. D, hopefully is obvious here, guys. Theorem 3.10. All right angles are what to each other? Well, they're all the same measure, guys. They're all 90 degrees, and angles that have the same measure are congruent to each other. So all right angles are congruent. How about theorem 3.11 now? Perpendicular lines form congruent adjacent angles. There was no blank to put right there. Really, and this diagram goes right back to where we were here. We have perpendicular lines, and adjacent angles, which aren't usually congruent, will be in this case. Angle 1 and angle 2 are adjacent, and because they're both 90, they are adjacent and congruent. And the same thing happens with angle 1 and angle 4. These two angles are adjacent, right next to each other, but also congruent. Usually in a case like this with intersecting lines, guys, you get a pair of adjacent angles like 5 and 6 that are adjacent but not congruent. It looks like in this diagram 5 is obtuse and 6 is acute. But if your lines are perpendicular, then your adjacent angles are also going to be congruent. Let me shrink this down just a second here, everybody. I think if I put a dot there, that does what I need it to do. Okay, two more theorems to take us home now. Theorem 3.12. If two angles here are congruent and supplementary, then each angle is a what? Okay, congruent means they have to be equal to each other. Supplementary means that they have to add up to 180. So if my first angle was x, and my second angle then, because it would be congruent to that angle, would have to be x as well, if they're supplementary, they'd have to add up to 180 degrees. Well, let's solve that equation, guys. We're going to combine our two like terms here to make a 2x is equal to 180. We'll divide both sides by 2. X has to equal 90. And what kind of angle is that? We are dealing with a right angle. All right, so if two angles are congruent and supplementary, each one of them has to be a right angle. And last one, if two congruent angles form a linear pair, then they are blank. Okay, to draw a linear pair, you just draw a line here, pick a point somewhere on it, and extend another ray sticking up out of it. But they're saying now that these two angles here, doesn't really look like it, I didn't draw it well, but they need to be congruent to each other. So if this is x degrees, this one would need to be x as well. And this equation is going to look familiar, guys. If they form a linear pair, that makes them supplementary. X plus x equals, 180, which is exactly the equation I just started with right here. And we're going to get to the exact same conclusion here. X is 90. So if two angles form a linear pair, then they are right angles. All right, guys. So that is really all we're going to cover right here in 3.6. It was a lot of writing, sorry about that, and a lot of theorems that have been introduced right here that are going to kind of form the basis of some things that we're going to do later on in Chapter 3, and actually we'll keep coming back to a lot of these ideas later on throughout the year. So good luck on your 3.6 homework, everybody. Let us know when you have some questions.